Picture this, a time before stars, before galaxies, before even light itself existed. The universe was a dark, formless expanse, waiting for its first spark. But what exactly was that first light, and where did it come from? Was it the brilliant burst of the Big Bang, the glow of the first stars forming, or perhaps something even more mysterious? For centuries, humanity has looked to the skies, searching for answers to our cosmic origins. Yet, the story of the universe's first light remains one of the greatest unsolved mysteries. Scientists, philosophers, and dreamers have proposed countless ideas, each offering a glimpse into how it all began. In this video, we're diving into 30 mind-bending theories about the universe's first light. From the widely accepted to the wildly speculative, we'll explore ideas that challenge everything we think we know about the cosmos. By the end, you'll see the universe in a new light, literally. Are you ready to uncover the secrets hidden in the stars? Let's get started. Let's start with the cornerstone of modern cosmology, the Big Bang theory. This widely accepted idea suggests that the universe began as an incredibly hot and dense point, expanding outward in a massive explosion. But what does this have to do with the universe's first light? Picture the early universe as a kind of cosmic soup too hot and dense for light to travel freely. For nearly 400,000 years after the Big Bang, the universe was essentially opaque, with particles constantly colliding and scattering light. Eventually, as the universe expanded and cooled, protons and electrons combined to form neutral atoms. This pivotal moment, known as recombination, allowed photons to break free and travel unobstructed for the first time. What we observe today as the cosmic microwave background, or CMB, is the ancient glow of this first light. It's like a snapshot of the universe when it was just a baby, around 380,000 years old. The CMB provides crucial evidence for the Big Bang, revealing subtle temperature variations that point to the seeds of galaxies and cosmic structures. But here's the fascinating part. This light isn't just ancient history. It's still all around us, stretching across the universe in every direction. By studying the CMB, scientists gain insights into the universe's origins, composition, and evolution. It's a reminder that even in the vast darkness of space, there are echoes of light from the dawn of time. As we delve deeper into the mystery of the universe's first light, the Big Bang theory sets the stage for much of what we'll explore next. But let's not stop here. There's so much more to uncover. Now that we've explored how the Big Bang set the stage for the universe's first light, let's dive into another groundbreaking concept that further enriches our understanding, the inflation theory. This theory suggests that just moments after the Big Bang, the universe underwent an extraordinary phase of rapid expansion, growing exponentially in a fraction of a second. Picture it like a cosmic balloon inflating at unimaginable speeds, smoothing out any irregularities and creating the vast, uniform space we observe today. During this brief but critical period, the universe expanded faster than the speed of light, not violating any laws of physics, as space itself was stretching rather than objects moving through it. This rapid expansion had profound implications for the distribution of the first light. As the universe stretched, tiny quantum fluctuations were magnified across vast distances, laying the groundwork for the cosmic structures we see today, including galaxies, stars, and planets. The inflation theory also helps explain why the cosmic microwave background appears so uniform in every direction. Without this rapid expansion, the universe would have been far too lumpy and uneven for light to spread so evenly. In essence, inflation acted as a cosmic iron, smoothing out the wrinkles in the early universe and setting the stage for the formation of the first light. But the story doesn't end there. Inflation theory also predicts that the universe might be far larger than we can observe, with regions beyond our cosmic horizon that are fundamentally different from what we know. This concept opens up exciting possibilities about the nature of the cosmos and how the first light might have played a role in shaping the universe's structure. By examining these ideas, we gain a deeper appreciation for the intricate dance of forces that led to the universe as we know it. As we continue our exploration, the inflation theory not only builds on the Big Bang, but also introduces new questions about the universe's true size and complexity. With each step, we uncover more about the cosmic puzzle, and the role of light in its creation becomes ever more fascinating. With the stage set by both the Big Bang and the inflation theory, let's zoom in on the microscopic level to uncover how quantum fluctuations played a crucial role in shaping the universe as we know it. Quantum fluctuations might sound like something out of science fiction, but they are real, tiny, temporary changes in the amount of energy in a point in space. In the extreme conditions of the early universe, these minuscule disturbances had a monumental impact. Imagine the infant universe as a bustling sea of energy, where quantum fluctuations caused slight variations in density. As the universe rapidly expanded during the inflationary phase, these microscopic ripples were stretched across vast distances, becoming the seeds of cosmic structure. These tiny imperfections acted like blueprints, dictating where matter would eventually gather and form the first stars, galaxies, and clusters. Without quantum fluctuations, the universe might have remained eerily smooth, lacking the density variations needed for gravity to pull matter together. It was these fluctuations that provided the initial spark, guiding the formation of the first light and setting the stage for the birth of stars and galaxies. In a sense, they were the universe's first architects, designing the cosmic landscape we observe today. The connection between quantum mechanics and cosmology in this context is nothing short of extraordinary. What began as random, subatomic wiggles in the fabric of spacetime grew into the grand cosmic structures that define our universe. This fascinating interplay between the smallest scales and the largest underscores just how intertwined every level of existence truly is. As we delve deeper into the origins of the universe's first light, these quantum fluctuations remind us that even the tiniest elements of reality can have the most profound consequences. This insight not only enriches our understanding of the cosmos, but also highlights the beauty of a universe where the microscopic and the massive are inextricably linked. With this concept in mind, we continue unraveling the layers of the universe's mystery, one quantum ripple at a time. Shifting our gaze beyond the confines of our universe, let us explore the mind-blowing concept of the multiverse hypothesis. This theory suggests that our universe is not alone, but is part of a vast cosmic landscape filled with countless other universes. Each of these universes could have its own unique physical laws, constants, and even the nature of light itself might differ dramatically from what we observe here. Picture a sea of infinite possibilities where every version of reality exists simultaneously, some vastly different from our own. In this context, what does the first light in our universe mean when compared to the potential first lights of other universes? The answer lies in the conditions that gave rise to light in the early moments of each universe. If the constants governing the strength of gravity or the speed of light vary across the multiverse, the emergence of the first light would differ as well. For instance, in a universe where light travels slower than in ours, the timeline for the first light might stretch longer, altering the cosmic history of that realm. Conversely, in a universe where light moves faster, this process could occur at an accelerated pace. The multiverse hypothesis opens up a realm of speculation and imagination, prompting questions about whether the first light in other universes resembles ours or takes on entirely different forms. Perhaps in some, the first light never emerges, leaving those universes shrouded in eternal darkness. Or in others, the first light might manifest as something completely unrecognizable to our senses, beyond the visible spectrum we know. Exploring this theory deepens our appreciation for the uniqueness of our universe's first light, while reminding us of the vast unknowns that lie beyond. While the multiverse remains speculative, it encourages us to think bigger, challenging the very boundaries of our understanding of existence. As we ponder the multiverse, we are reminded that our universe's first light is but one chapter in an even grander cosmic story. Moving from the expansive possibilities of the multiverse, let us now turn our attention to a theory that once held significant sway in the scientific community, the steady-state theory. Unlike the dynamic beginnings proposed by the Big Bang or multiverse hypotheses, this theory suggests a universe that has always existed and will continue to exist without any definitive start or end. In other words, there was no first light in the traditional sense, but rather a continuous creation of matter and energy throughout the cosmos. The steady-state model was popularized in the mid-20th century as an alternative to the Big Bang theory. It postulated that while galaxies and stars may move apart due to the universe's expansion, new matter is continuously generated to fill the voids. This ongoing process ensures the universe maintains a constant density and appearance over time. In this framework, light does not have a singular origin point. Instead, it emerges gradually and continually as part of the universe's natural evolution. How does this concept address the mystery of the universe's first light? Interestingly, the steady-state theory bypasses the need for a grand cosmic event like the Big Bang. Light, in this view, isn't tied to a singular moment of creation, but is rather an ever-present phenomenon that evolves alongside the universe itself. Proponents of the theory argued that this approach avoided the complexities of explaining how all matter and energy could emerge from a single point in time. Although the steady-state theory has been largely discredited due to evidence supporting the Big Bang, such as the discovery of the cosmic microwave background radiation, it remains an important stepping stone in our understanding of the cosmos. It challenged scientists to refine their models and highlighted the importance of considering alternative explanations. By exploring the steady-state perspective, we gain insight into the evolving nature of cosmological thought and the critical role played by historical theories in shaping modern science. Even though it doesn't align with current observations, its legacy reminds us that questioning the boundaries of knowledge is essential to uncovering the truth about the universe's first light. Shifting our focus to a theory that takes us deep into the heart of the cosmos, let's explore the plasma universe theory. This concept challenges traditional models by placing plasma and electromagnetic forces at the forefront of the universe's early development. Unlike the more widely accepted gravitational models, the plasma universe theory suggests that these electrically charged particles and their interactions were fundamental in shaping the cosmos and, importantly, in the emergence of the universe's first light. At its core, the plasma universe theory argues that plasma, which makes up over 99% of the visible universe, played an essential role in the formation of galaxies, stars, and even the first light. Plasma, as you may recall, is the fourth state of matter, characterized by high-energy particles that respond strongly to electromagnetic fields. During the universe's earliest moments, these electromagnetic forces may have influenced the distribution of matter in ways that traditional models fail to account for. Imagine an early universe filled with swirling, electrified gas clouds. These plasma formations would have interacted with magnetic fields, creating complex networks of filaments and structures. These interactions, according to plasma universe proponents, could have been the driving force behind the organization of matter, leading to the creation of the first luminous objects. The light we see as the cosmic microwave background, then, might not only be the result of a single explosive event, but also the product of ongoing electromagnetic processes. Moreover, the theory suggests that the behavior of plasma could explain some of the large-scale structures we observe today, such as the filaments connecting galaxies. Instead of relying solely on gravity, the plasma universe theory incorporates electromagnetic forces, painting a richer picture of cosmic evolution. This perspective raises intriguing questions about how we interpret the universe's first light. Could it be more than just the afterglow of a singular event? Could it also reflect the complex interplay of plasma dynamics in the universe's infancy? Although the plasma universe theory remains controversial and lacks widespread acceptance, it adds another layer of complexity to our understanding of the cosmos. By considering alternative forces at play, this theory invites us to rethink the origins of light and the fundamental processes that shaped our universe. As we delve deeper into these ideas, we begin to see how even the most unexpected forces may hold secrets to the universe's beginnings. So, what role does plasma truly play in this cosmic puzzle? The answer may redefine our understanding of the universe's first light. Venturing into one of the most mind-bending corners of cosmological thought, let's examine the holographic principle. This theory presents a radical perspective on the nature of reality itself, suggesting that the universe may be nothing more than a projection, a three-dimensional image encoded on a two-dimensional surface at its edge. While this might sound like something out of science fiction, it is actually rooted in serious physics with implications for understanding the universe's first light. The holographic principle stems from insights gained in black hole research. Scientists discovered that the information contained within a black hole is not stored in its three-dimensional interior, but instead etched onto its two-dimensional event horizon. Extending this idea to the cosmos, the principle proposes that all the information in our universe could similarly be encoded on a vast, distant boundary that surrounds it. If true, this concept challenges everything we think we know about space, time, and matter. So, how might the holographic principle relate to the first light? Well, consider this. If the universe is essentially a hologram, then the cosmic microwave background, our best record of the universe's earliest moments, might be akin to a projection from the cosmic surface onto the three-dimensional space we perceive. In other words, the light we observe might not just be an echo of the Big Bang, but also a manifestation of the intricate encoding processes inherent in this holographic framework. This idea opens up fascinating possibilities about the nature of the first light. Perhaps it isn't merely a remnant of a singular event, but part of a deeper informational structure embedded in the fabric of the cosmos. If the universe is a hologram, then the light we detect may carry clues to these underlying blueprints, offering a new lens through which to interpret the origins of the universe. Of course, the holographic principle remains speculative and not yet proven. Yet, it invites us to stretch our imaginations and consider alternative ways of thinking about the cosmos. By merging cutting-edge physics with philosophical inquiry, this theory reminds us that even the most basic questions like the nature of light can lead to extraordinary insights into the workings of the universe. Shifting gears to a fascinating alternative to the traditional Big Bang model, let's explore the cyclic model, a theory proposing that the universe does not have just one beginning, but instead exists in an endless series of expansions and contractions. Imagine the cosmos as a massive, breathing entity where each breath corresponds to a cycle of birth, growth, and collapse. According to this idea, the universe periodically contracts into an unimaginably dense state, only to rebound and expand once more, creating a new era. At the heart of the cyclic model lies the hypothesis that the Big Bang is not a singular event but part of an ongoing process. In this framework, the cosmic microwave background, the faint glow left over from the Big Bang, might not represent the absolute origin of the universe but rather the aftermath of the most recent cycle. Each phase of contraction and expansion could leave its own imprint on the light we detect, offering tantalizing clues about previous cycles. Now, how does this relate to the first light? Under the cyclic model, the light we observe today might carry echoes from earlier cycles, hidden within its intricate patterns. These echoes could provide insights into the conditions of past epochs, potentially reshaping our understanding of the universe's history. Moreover, if the universe truly cycles through infinite rounds, the concept of first light becomes more nuanced. It might not be the result of a single, definitive event, but rather a recurring phenomenon, appearing anew with each expansion phase. Critics of the cyclic model point to challenges in aligning it with observations of the universe's current state. Yet, proponents argue that it offers a compelling alternative to singular event theories, inviting us to think beyond linear timelines. By considering the universe as something endlessly renewing, the cyclic model sparks profound questions about the nature of time, existence, and the origins of light itself. Could the cosmos be telling us a story far deeper and more cyclical than we've ever imagined? As we delve further into this theory, we begin to uncover layers of complexity that push the boundaries of our cosmic understanding. With this in mind, it's clear that the story of the universe's first light may be richer and more intricate than ever anticipated. As we continue our journey through these theories, let's keep an open mind to the endless possibilities the cosmos has to offer. Building on our exploration of cyclical possibilities, let's journey into another groundbreaking theory that reimagines the origins of our universe, the ekpyrotic universe. This concept suggests that the universe wasn't born from a singular Big Bang, but instead emerged from a colossal collision between higher dimensional entities known as branes. To visualize this, imagine vast, flat membranes floating in an invisible, multidimensional space. When these branes collide, their interaction unleashes an unprecedented amount of energy, giving rise to the cosmos as we know it. In the ekpyrotic model, the universe's first light would stem directly from the energy released during this high-energy collision. Picture it like two cosmic sheets violently smashing together, creating ripples of immense heat and light that eventually coalesce into the stars, galaxies, and cosmic structures we see today. This scenario provides an alternative explanation for the cosmic microwave background, proposing that it might represent the aftermath of brane interactions rather than a singular explosion. What's particularly intriguing about the ekpyrotic universe theory is how it addresses some of the gaps left by traditional models. For instance, it offers explanations for why the universe appears so uniform on large scales and why certain features, such as slight temperature variations in the cosmic microwave background, exist. By introducing extra dimensions into the equation, this theory opens up new avenues for understanding the fundamental nature of space, time, and light. Critics raise valid concerns about the ekpyrotic model, pointing out challenges in testing its predictions. However, its proponents highlight its potential to bridge gaps in current cosmological understanding, pushing the boundaries of how we perceive the universe's origins. Could the first light we observe today be the remnant of a monumental brane collision? The idea reshapes our perception of the universe's genesis, inviting us to explore dimensions beyond the familiar three. As we continue our deep dive into theories about the universe's first light, the ekpyrotic universe presents yet another fascinating possibility, challenging our assumptions and inspiring further curiosity. Shifting our focus to a truly mind-bending possibility, let's delve into the black hole genesis theory, a hypothesis suggesting that our universe could have originated from a black hole in another universe. Imagine the cosmos as an interconnected web where the birth of one universe stems from the death of another. In this scenario, black holes, which we traditionally view as cosmic endpoints, serve as gateways to entirely new beginnings. The theory begins with the premise that when a massive star collapses into a black hole, the gravitational forces within may cause an implosion so powerful that it spawns a brand new universe. Think of it like a seed being planted in the fertile soil of another realm. The singularity at the heart of the black hole might trigger conditions ripe for creating not just stars and galaxies, but entire dimensions. If true, our universe's first light could be the direct result of this extraordinary process, emerging as the echoes of an ancient cosmic event. What makes this idea so captivating is its potential to explain some of the most puzzling aspects of the universe's behavior. For instance, it addresses the question of why the laws of physics seem so finely tuned for life to exist. Perhaps our universe inherited these properties from its parent universe, much like genetic traits are passed down through generations. Moreover, the black hole genesis theory implies that our universe might someday give rise to others, continuing an endless cycle of creation. While fascinating, this concept presents significant challenges for verification. Scientists must develop advanced tools capable of detecting traces left behind by the supposed parent black hole. Yet, the implications of such a theory are profound, redefining our understanding of space, time, and even existence itself. Could the light we observe today, billions of years later, be the legacy of an interdimensional birth? Let's keep exploring as we uncover the next layer in our quest for the universe's first light. Transitioning from the mind-bending concept of black holes birthing universes, let us now venture into an equally provocative and intriguing theory, the simulation hypothesis. This controversial idea suggests that our entire universe might not be a naturally occurring entity, but rather a sophisticated simulation crafted by an advanced intelligence. If this hypothesis holds any truth, then the universe's first light may not arise from natural cosmic processes, but instead be a deliberately programmed phenomenon within this grand simulation. Imagine a scenario where the cosmic microwave background, often considered the afterglow of the Big Bang and the universe's first observable light, is not the result of a primordial explosion, but instead a carefully designed element within a simulated environment. The light we perceive could represent predetermined parameters set by the creators of the simulation to mimic a natural universe. In this context, the patterns and distributions of the first light might reflect the underlying code or algorithms governing the simulation rather than the chaotic beginnings of a physical universe. What makes the simulation hypothesis particularly fascinating is how it challenges our traditional understanding of reality and existence. Proponents argue that the universe exhibits characteristics consistent with a computer simulation, such as quantized phenomena and fundamental constants that appear eerily precise. Could the fine-tuning of these constants, which allow for life as we know it, be the result of deliberate programming choices? Furthermore, if the universe is indeed simulated, the first light could serve as a marker or signal embedded within the simulation to leave clues for its inhabitants. Critics of the hypothesis raise valid concerns, pointing out the lack of empirical evidence supporting the notion of a simulated universe. However, the idea continues to spark heated debates and inspire novel lines of inquiry. Scientists contemplate whether anomalies in cosmic observations, such as peculiar alignments or unexplained phenomena, might hint at the universe's artificial origins. If future research uncovers traces of programming artifacts or patterns inconsistent with natural processes, the implications would profoundly reshape our understanding of everything, from physics to metaphysics. As we continue our exploration, the simulation hypothesis offers a tantalizing perspective, inviting us to question the very nature of the light that illuminates our cosmos. Could the universe's first light hold secrets not just of its origin, but also of its potential artificial creation? Shifting gears to another groundbreaking theory, let's explore the string theory landscape and its implications for the universe's first light. String theory posits that the fundamental constituents of the universe are not particles but rather minuscule, vibrating strings. These strings, existing in multiple dimensions beyond the familiar 3 of space and 1 of time, could profoundly shape the nature of the cosmos and, by extension, the first light. In the string theory landscape, the fabric of reality may consist of countless universes, each governed by a unique set of physical laws arising from different configurations of these strings. This multiverse framework suggests that our universe is just one bubble in an immense cosmic foam, with variations in fundamental constants across different regions. If this is true, the properties of the first light we observe might reflect the specific conditions of our slice of the multiverse rather than universal absolutes. Imagine a scenario where the cosmic microwave background, traditionally viewed as evidence of the Big Bang, is influenced by the interplay of string vibrations. The tiny fluctuations in temperature and density could correspond to the resonances of these fundamental strings, painting a picture of the early universe as a symphony of oscillations rather than a simple explosion. This perspective adds depth to our understanding of the first light, suggesting it carries signatures of higher dimensions and alternative realities. Moreover, string theory offers explanations for phenomena that traditional models struggle to address, such as the unification of quantum mechanics and gravity. If true, the first light might encode remnants of this unification, revealing insights into the earliest moments of the cosmos when all forces were unified. As research progresses, scientists hope to uncover whether patterns in the cosmic microwave background point toward string theory's predictions, potentially reshaping our comprehension of the universe's origins. While speculative, the string theory landscape expands our horizons, challenging us to imagine a reality far richer and more complex than previously thought. Could the universe's first light be a window into this intricate tapestry of dimensions and possibilities? The journey to uncover these truths continues, promising new revelations at every turn. Turning our attention to another fascinating aspect of the universe's first light, let's delve into the potential influence of dark matter. While dark matter does not emit, absorb, or reflect light, its gravitational effects have a profound impact on the cosmos, including the formation and distribution of the first light. Dark matter makes up roughly 84% of the universe's mass, creating an invisible scaffold that guides the assembly of galaxies and large-scale structures. In the early universe, these dark matter concentrations acted as gravitational wells, drawing in ordinary matter and facilitating the formation of the first stars and galaxies. As this process unfolded, the resulting structures influenced the path and spread of the first light, effectively shaping the cosmic web we observe today. A key insight into dark matter's role comes from the cosmic microwave background, the afterglow of the Big Bang. Subtle variations in temperature across the CMB reflect the influence of dark matter at the universe's infancy. These fluctuations, caused by the interplay between dark matter, ordinary matter, and radiation, reveal how dark matter's gravitational pull helped to concentrate matter into dense regions. This concentration, in turn, set the stage for the formation of luminous objects and the subsequent release of the first light. Moreover, current models suggest that dark matter might have altered the opacity of the early universe. By influencing the balance between photons and matter, dark matter could have affected how quickly the universe became transparent, a critical moment known as recombination. This transparency allowed the first light to travel freely, eventually reaching us as the cosmic microwave background. Despite its mysterious nature, dark matter's indirect role in the universe's first light offers a window into the cosmic processes that shaped the early universe. Observations and simulations continue to refine our understanding of how dark matter's gravitational influence choreographed the emergence of light in the cosmos. What remains clear is that the story of the universe's first light is deeply intertwined with the enigmatic pull of dark matter, a force that continues to challenge and inspire scientists worldwide. Shifting our focus now to another intriguing theory, let's explore the role of primordial black holes in shaping the universe's first light. Unlike black holes formed from the collapse of massive stars, primordial black holes are thought to have emerged shortly after the Big Bang during the universe's earliest moments. These theoretical objects could range in size from microscopic to several times the mass of the Sun, with their origins tied to extreme density fluctuations in the newborn cosmos. The formation of these black holes would have occurred under conditions vastly different from those today. Regions of the early universe that were particularly dense could have collapsed under their own gravity, creating these primordial entities. Their presence would have influenced the behavior of surrounding matter and radiation, potentially altering the emergence and propagation of the first light. One of the ways primordial black holes might have affected the first light is through their interactions with the cosmic microwave background. As these compact objects distorted spacetime, they could have caused gravitational lensing effects, subtly altering the CMB's pattern. This lensing would have stretched and magnified certain regions of the background radiation, leaving imprints that could still be detectable today. Additionally, if primordial black holes evaporated through a process known as Hawking radiation, they could have released bursts of energy into the early universe. These bursts might have influenced the ionization state of the cosmic plasma, affecting how quickly the universe became transparent. Such interactions could have played a crucial role in determining when the first light was able to travel freely. The existence of primordial black holes remains speculative, but their potential impact on the early universe highlights the intricate dance between matter, energy, and gravity. By studying the cosmic microwave background and other cosmic phenomena, scientists continue to search for evidence that might confirm or refute this fascinating theory. Whether or not these ancient black holes truly existed, their hypothesized influence adds yet another layer of complexity to our understanding of the universe's first light. Transitioning now to another fascinating aspect of the early universe, let's delve into the cosmic neutrino background, a lesser-known counterpart to the widely discussed cosmic microwave background. While photons dominate the conversation surrounding the universe's first light, neutrinos played a crucial role in shaping the early cosmos. These nearly massless particles, often dubbed ghost particles, were also abundant in the early universe and might have left their mark on the emergence of the first light. The cosmic neutrino background, or CNUB, consists of relic neutrinos that decoupled from matter just seconds after the Big Bang. At this point, the universe was so hot and dense that neutrinos were constantly interacting with other particles. However, as the universe expanded and cooled, neutrinos ceased their interactions, forming a cosmic sea of neutrinos still permeating the universe today. Unlike photons, detecting these neutrinos is incredibly challenging due to their weak interactions with matter, making them a mysterious presence in cosmology. Despite their elusive nature, neutrinos could have significantly influenced the dynamics of the early universe. Their presence would have affected the rate of expansion and the behavior of matter in the newborn cosmos. One of the ways they might have impacted the first light is through their role in cosmic plasma. Neutrinos contributed to the overall energy density of the universe, subtly altering the density fluctuations that eventually led to the formation of cosmic structures. This could have influenced the timing and nature of the transition from an opaque plasma to a transparent universe. Moreover, the cosmic neutrino background might also have affected the cosmic microwave background itself. Through their gravitational influence, relic neutrinos could have contributed to the patterns observed in the CMB, adding another layer of complexity to the interplay of forces that shaped the first light. Although detecting the CNUB directly remains a formidable challenge, indirect evidence from cosmic observations continues to refine our understanding of these ghostly particles and their role in the early universe. Exploring the cosmic neutrino background not only expands our knowledge of the universe's first light, but also sheds light on the fundamental forces and particles that govern the cosmos. By unraveling the secrets of neutrinos, scientists hope to uncover new insights into the early universe's conditions and the intricate balance that led to the emergence of the first light. Shifting our focus now to one of the most profound questions in cosmology, let's examine the Baryon asymmetry problem, a mystery that delves into why our universe is predominantly made of matter instead of antimatter. In theory, the Big Bang should have produced equal amounts of matter and antimatter, as these particles are created in pairs according to fundamental physics. However, observations reveal a stark imbalance. The universe is overwhelmingly composed of matter, with barely any antimatter present. This discrepancy has puzzled scientists for decades and holds significant implications for the nature of the universe's first light. To understand this phenomenon, we must first recognize what baryons are. Baryons, such as protons and neutrons, form the building blocks of visible matter in the universe. During the earliest moments after the Big Bang, when energies were unimaginably high, particles and antiparticles continuously formed and annihilated each other. Yet somehow, a tiny fraction of matter survived this cosmic dance of creation and destruction. This surviving matter became the primary ingredient for stars, galaxies, and all the structures we observe today. The implications of this asymmetry extend to the emergence of the first light. If the universe had contained equal amounts of matter and antimatter, their annihilation would have resulted in a sea of pure energy, leaving little to no opportunity for stars and galaxies to form. The survival of matter allowed for the formation of cosmic structures, creating conditions necessary for the universe to transition from an opaque plasma to a transparent state, giving rise to the first light. Several hypotheses attempt to explain this imbalance. One leading idea is that processes occurring during the universe's earliest moments violated the principle of symmetry between matter and antimatter. These processes, referred to as CP violation, could have favored the creation of slightly more matter over antimatter. While current understanding explains some aspects of this asymmetry, gaps remain, driving physicists to explore new theories and experimental evidence. Understanding the baryon asymmetry problem is crucial because it helps us unravel the conditions that enabled the first light to emerge. By investigating the mechanisms that caused this imbalance, we gain insights into the fundamental forces governing the universe and the delicate balance that allowed our cosmos to develop into the vibrant, star-studded expanse we see today. As research progresses, every clue brings us closer to understanding not only the mystery of matter, but also the story of the universe's first light. Moving forward, let us delve into a fascinating yet speculative idea that could reshape our understanding of the universe's expansion and the conditions for the first light: the concept of phantom energy. Phantom energy represents an extreme form of dark energy, a mysterious force driving the accelerated expansion of the universe. Unlike conventional dark energy, which maintains a constant density as the universe expands, phantom energy grows stronger over time, eventually leading to a dramatic and possibly catastrophic end for the cosmos. To comprehend phantom energy's implications for the first light, it is essential to consider its effect on the universe's large-scale structure. In scenarios where phantom energy dominates, the universe's expansion rate increases exponentially. This rapid acceleration could have influenced the early universe's evolution, altering the timeline and conditions under which the first light appeared. Specifically, such an intense expansion might have delayed the formation of cosmic structures, such as galaxies and stars, which are necessary for the first light to emerge. The presence of phantom energy in the early universe may also have impacted the cosmic microwave background, the relic radiation from the Big Bang that constitutes the universe's first observable light. If phantom energy's influence was significant during the radiation-dominated era, it could have subtly altered the temperature fluctuations and anisotropies in the CMB. These changes, though slight, would provide valuable clues about the conditions during the universe's infancy and the role of dark energy in shaping the first light. Moreover, the phantom energy model raises intriguing questions about the long-term fate of the universe and its initial moments. In the most extreme scenarios, phantom energy could result in what scientists term a big rip, where the expanding force grows so strong that it eventually tears apart galaxies, stars, and even atomic structures. Although this catastrophic outcome would occur far in the future, its theoretical framework offers insights into the balance of forces at play during the universe's early stages. By exploring phantom energy, we uncover a tantalizing possibility that the forces governing the universe's ultimate fate also played a critical role in its very beginning. Understanding these dynamics helps us piece together the intricate puzzle of the universe's first light, adding depth to our comprehension of the cosmos's origins. As we continue this exploration, the interplay between dark energy and the early universe's development becomes increasingly significant, opening doors to groundbreaking discoveries about the nature of existence itself. From here, we can turn our attention to yet another captivating theory that challenges conventional wisdom: how consciousness itself might have been involved in the emergence of the first light. But first, let us reflect on the profound implications of phantom energy and its potential to redefine our understanding of the universe's expansion. Now, let us shift our focus to a thought-provoking concept that intertwines the universe's structure with the conditions necessary for life itself: the anthropic principle. This principle suggests that the fundamental constants and initial conditions of the universe are finely tuned to allow for the existence of life. When applied to the first light, it prompts us to consider how the emergence of this primordial radiation may have been influenced by these life-friendly conditions. To understand this better, imagine the universe as a delicate system of interconnected gears. Each gear represents a fundamental constant, such as the strength of gravity, the speed of light, or the charge of an electron. If any of these gears were too large or too small, the entire system would collapse, rendering the universe incapable of supporting life as we know it. The first light, originating from the cosmic microwave background, is a direct result of this intricate balance. It not only reveals the universe's early conditions, but also underscores the necessity of these conditions for life to eventually arise. The anthropic principle offers two main perspectives: the weak version and the strong version. The weak anthropic principle states that the universe appears as it does because we observe it. Any other universe incompatible with observers simply would not be observed. In this sense, the first light is viewed as a natural consequence of a universe capable of hosting life. The strong anthropic principle, however, goes further, suggesting that the universe must produce life, not just allow for it. Under this lens, the emergence of the first light could be seen as a prerequisite step in the inevitable development of life-supporting environments. Moreover, the anthropic principle invites us to explore the idea of a multiverse, where countless universes exist with varying constants and conditions. In most of these universes, the delicate balance necessary for the first light and life would not exist. Our universe, with its precise tuning, stands out as an extraordinary exception. This perspective deepens the mystery of the first light, framing it not just as a scientific phenomenon, but also as a cosmic enigma tied to the very possibility of our existence. As we ponder the anthropic principle, we begin to see the universe's structure and the nature of the first light through a new lens, one that emphasizes the profound connection between life and the cosmos. This perspective enriches our understanding of the universe's origins, offering a compelling narrative that bridges the gap between the scientific and the philosophical. With this fascinating theory in mind, let us now turn our attention to another intriguing possibility: the role of quantum gravity in shaping the universe's first light. Let us now embark on a journey into one of the most profound quests in modern physics: the unification of quantum mechanics and gravity, a concept known as quantum gravity. This ambitious pursuit seeks to bridge the gap between the smallest scales of reality, governed by quantum mechanics, and the largest cosmic phenomena dominated by gravity. By exploring how quantum gravity might explain the universe's first light, we open a window into the fundamental nature of space, time, and the cosmos itself. Quantum gravity represents the ultimate dream of physicists, creating a single, cohesive framework that describes all the forces in the universe. In the context of the first light, this theory becomes particularly intriguing. The cosmic microwave background, which we observe as the universe's earliest radiation, emerged when the universe was just 380,000 years old. At that time, the universe was transitioning from a state where matter and energy were tightly coupled to one where light could finally travel freely. But what about the moments before this milestone? What governed the universe during its earliest, most chaotic phases? Here, quantum gravity comes into play. By attempting to understand gravity at the quantum level, physicists hope to shed light on the conditions present in the universe's infancy. One possibility is that quantum gravity effects smoothed out the initial irregularities in the fabric of spacetime, creating a more uniform backdrop for the first light to emerge. This smoothing process could have influenced the distribution of matter and energy, setting the stage for the universe's later evolution. Moreover, quantum gravity theories such as loop quantum gravity or string theory suggest that spacetime itself may have had a granular structure at extremely small scales. This granularity could have left imprints on the cosmic microwave background, offering clues about the universe's earliest moments. These imprints, if detected, would provide direct evidence of quantum gravity's influence on the first light. The quest for quantum gravity not only deepens our understanding of the universe's origins, but also challenges us to think beyond conventional boundaries. It invites us to imagine a universe where the rules of physics as we know them are just the tip of a vast, intricate iceberg. As we continue to explore this idea, the mystery of the first light takes on a new dimension, one that ties together the smallest particles and the largest structures in a single, elegant framework. With this in mind, we move forward to uncover yet another layer of the cosmic puzzle, the cosmic strings hypothesis. Transitioning from the intricate world of quantum gravity, let us now venture into another fascinating realm of cosmology, the cosmic strings hypothesis. Imagine the early universe as a vast, chaotic canvas filled with energetic forces. Within this canvas, some theories suggest that immense, thread-like structures known as cosmic strings could have formed, remnants of the universe's earliest moments. These hypothetical entities, far thinner than an atom yet possessing immense mass and energy, might have played a crucial role in shaping the universe's first light. Cosmic strings are not your everyday strings. Instead, they are theorized to be incredibly dense, one-dimensional objects that formed during phase transitions in the early universe, similar to how cracks form in ice as water freezes. If these strings indeed existed, their immense gravitational pull could have influenced the distribution of matter and radiation in the infant cosmos. As the universe expanded and cooled, these strings may have left imprints on the cosmic microwave background, subtly altering the patterns of the first light we observe today. One of the most intriguing aspects of cosmic strings is their potential to generate gravitational waves. These ripples in spacetime, first predicted by Einstein's theory of general relativity, could carry signatures of cosmic strings from the earliest epochs of the universe. If detected, such gravitational waves would provide direct evidence of these enigmatic structures and offer valuable insights into the conditions that shaped the first light. Moreover, cosmic strings might also help explain some of the large-scale structures we observe in the universe, such as galaxies and galaxy clusters. By acting as seeds for cosmic filaments, these strings could have guided the formation of the universe's intricate web of matter, influencing both the distribution of the first light and the evolution of cosmic structures. Delving further into this hypothesis, scientists continue to refine models and search for observational evidence. While the existence of cosmic strings remains speculative, their potential impact on the universe's first light makes them a captivating subject of study. With this in mind, we now turn our attention to yet another intriguing possibility: the variable speed of light theory and its implications for the first light's origins. Shifting our focus from cosmic strings, let us now explore a theory that challenges one of the most fundamental principles of physics, the constancy of the speed of light. Known as the variable speed of light theory, or VSL, this controversial idea suggests that the speed of light might not have always been the unchanging constant we know it as today. Instead, proponents argue that in the early universe, light may have traveled much faster than it does now, a concept that could revolutionize our understanding of the first light and the universe's earliest moments. At its core, the VSL theory attempts to address some of the long-standing mysteries in cosmology, such as the horizon problem. This problem arises from the observation that distant regions of the universe appear to have uniform temperatures, despite being too far apart to have ever interacted if the speed of light has always been constant. By allowing light to travel faster in the early universe, the VSL theory provides an elegant solution. In this scenario, these distant regions would have had enough time to exchange energy and reach thermal equilibrium before the speed of light slowed to its current value. Moreover, the implications of a variable speed of light extend beyond solving the horizon problem. If correct, this theory could also explain other puzzling phenomena, such as the flatness problem and the distribution of the cosmic microwave background radiation. A faster speed of light in the early universe would have allowed for a more efficient spreading of energy and matter, creating the smooth, uniform conditions we observe today. Critics, however, point out that the VSL theory is still speculative and lacks direct observational evidence. It also requires significant modifications to established physical laws, which makes it a challenging concept to integrate into our current understanding of the universe. Nevertheless, the potential insights offered by this theory make it an exciting area of research. Looking deeper, the VSL theory challenges us to rethink the fundamental constants of nature and their role in shaping the cosmos. Could the speed of light have been a variable rather than a constant during the universe's infancy? If so, how might this have influenced the emergence of the first light and the overall structure of the universe? These questions invite further exploration and highlight the ongoing quest to unravel the mysteries of our cosmic origins. As scientists continue to test this theory, the answers could provide groundbreaking revelations about the universe's earliest light. Transitioning from the intriguing variable speed of light theory, we now journey into a cosmic concept that stretches the boundaries of our imagination, the eternal inflation theory. This theory suggests that inflation, the rapid expansion of the universe following the Big Bang, is not a singular event with a clear beginning and end, but rather an ongoing process that continues infinitely in some regions of the universe. If true, this means that while our observable universe has experienced a single inflationary epoch, there could be countless other regions where inflation is still actively occurring. The implications of eternal inflation for the universe's first light are profound. In regions where inflation persists, the conditions necessary for the emergence of light as we know it may never fully materialize. Conversely, in areas where inflation has ceased, the first light might manifest in entirely different ways, influenced by the unique properties of that specific pocket universe. This idea challenges the notion of a uniform cosmic history and suggests that the first light could vary dramatically across different parts of the multiverse. Moreover, eternal inflation raises fascinating questions about the nature of parallel universes. If inflation never ends, it implies the existence of an infinite number of universes, each with its own set of laws and physical constants. In some of these universes, the first light might appear at different times or even take forms entirely alien to our understanding. This diversity of cosmic beginnings could mean that the concept of first light itself is relative, depending on the specific universe in question. Critics of eternal inflation argue that the theory is speculative and lacks direct observational evidence. However, it offers a compelling framework for explaining the vast diversity of the cosmos and the potential existence of alternate realities. By considering the possibility that inflation never truly ends, we open the door to a universe or multiverse where the first light is not a singular event but a spectrum of beginnings, each with its own story to tell. As scientists continue to explore this theory, the answers could redefine our understanding of the universe's earliest moments and the infinite possibilities that lie beyond our observable horizon. Shifting our focus now to a groundbreaking proposal within the realm of particle physics, let's delve into the implications of supersymmetry on the universe's first light. Supersymmetry, often abbreviated as SUSY, is an elegant theoretical framework that suggests every known fundamental particle has a corresponding superpartner with differing properties. This extension of the Standard Model aims to resolve several mysteries in physics, including the nature of dark matter and the unification of forces. When applied to the context of the universe's first light, supersymmetry introduces fascinating possibilities. During the early moments of the cosmos, when temperatures were unimaginably high, particles and their superpartners may have coexisted in equilibrium. As the universe expanded and cooled, these superpartners could have played a crucial role in shaping the distribution of energy and matter, influencing the conditions under which the first light emerged. One significant aspect of supersymmetry is its potential to address the hierarchy problem, which questions why gravity is so much weaker than other forces. Resolving this issue impacts our understanding of the early universe's dynamics, including the formation and behavior of particles during the phase when light first began to propagate freely. Additionally, the theory predicts the existence of neutralinos, hypothetical particles that could constitute dark matter. If these neutralinos were abundant in the early universe, they might have interacted with photons, subtly altering the characteristics of the first light. Critics, however, highlight the lack of experimental evidence for supersymmetric particles despite extensive searches at particle accelerators like the Large Hadron Collider. Yet the theoretical allure of supersymmetry persists, as it unifies seemingly disparate phenomena and offers a richer tapestry of particles to explore. In the context of the first light, supersymmetry opens doors to a more intricate and interconnected picture of the universe's earliest moments. By considering this possibility, we deepen our appreciation for the complexity and beauty of cosmic origins, inviting us to reflect on how even the smallest particles may have contributed to the grand illumination of the cosmos. Moving on from the intriguing implications of supersymmetry, let us direct our attention to another captivating theory that might shed light on the universe's earliest moments, the action dark matter theory. Actions are hypothetical particles that were initially proposed to address a problem in quantum chromodynamics, the theory describing the strong force that binds atomic nuclei. Over time, these particles have become strong contenders for explaining dark matter, a mysterious substance that makes up roughly 27% of the universe but remains invisible to direct detection. If actions indeed comprise dark matter, their presence in the early universe could have profoundly influenced the conditions under which the first light emerged. These ultralight particles, if they exist, would have interacted with the primordial plasma that filled the cosmos shortly after the Big Bang. Their subtle interactions may have played a role in shaping the distribution of photons, potentially affecting the temperature fluctuations we observe today in the cosmic microwave background radiation. This radiation, often regarded as the afterglow of the Big Bang, represents the universe's first light and contains invaluable clues about its origins. The unique properties of actions suggest they could have contributed to the formation of cosmic structures. By clustering together under the force of gravity, actions might have acted as seeds for the growth of galaxies, influencing the environment in which the first light propagated. Furthermore, their hypothesized interactions with photons might have altered the polarization patterns of the cosmic microwave background, leaving faint but detectable imprints that future experiments could uncover. Despite their potential significance, actions remain elusive. researchers around the globe are currently developing innovative experiments designed to detect these particles, using techniques that range from microwave cavities to haloscopes. Should these efforts succeed, the discovery of actions would not only represent a monumental breakthrough in particle physics, but also provide critical insights into the universe's evolution and the nature of its first light. By considering the action dark matter theory, we expand our understanding of the intricate interplay between dark matter and the cosmic phenomena that define our universe. Shifting our focus to a concept that challenges even the most fundamental aspects of our understanding of the universe, let's delve into the theory of time before time. This theory posits the intriguing idea that time itself might not have existed in the way we perceive it before the emergence of the universe's first light. To comprehend this, we must first consider what time truly is. In our everyday experience, time flows in a linear, predictable manner, but in the realms of quantum mechanics and cosmology, the nature of time becomes far more complex and less intuitive. If we entertain the notion that time had a beginning, this raises profound questions about the origins of the universe and the conditions under which the first light emerged. If there was a before time, what did it look like? Scientists theorize that in the earliest moments of the universe, the concept of time as we know it may not have applied. Instead, the universe might have existed in a state where conventional time did not exist, perhaps resembling a timeless quantum realm. The implications of such a theory are vast. If time began with the Big Bang, then the emergence of the universe's first light could be seen as the moment when time itself started ticking forward. In this context, the cosmic microwave background radiation, often regarded as the universe's first light, represents not only the remnants of the Big Bang, but also the inception of time as a fundamental property of the cosmos. Moreover, this perspective challenges traditional views of causality. If there was no time, how could events occur, and how did the conditions for the universe's formation come to be? Some theorists propose that the laws of physics might allow for a state of timeless existence, where all possibilities coexist simultaneously until a trigger, such as the Big Bang, sets the universe into motion and establishes the flow of time. Exploring this theory enriches our understanding of the universe's origins by considering the possibility that the first light was not merely a consequence of physical processes, but also the starting point of time itself. By pondering such ideas, we gain new insights into the interconnected nature of the cosmos and the profound mysteries that continue to inspire scientific inquiry. This perspective invites us to reconsider not only the universe's first light, but also the very fabric of reality that governs our existence. Moving beyond the enigmatic concept of time before time, let's now explore another fascinating possibility that takes us into the realm of quantum mechanics. This brings us to the quantum entanglement hypothesis, which offers a unique perspective on how the universe's first light might have been influenced by some of the strangest properties of the quantum world. Quantum entanglement is a phenomenon where two particles become so deeply interconnected that the state of one instantly affects the state of the other, regardless of the distance between them. Imagine this as an invisible thread that links particles across vast expanses, defying our intuitive understanding of space and time. In the context of the early universe, scientists hypothesize that this entanglement might have played a significant role in shaping the universe's first light. During the universe's infancy, when conditions were unimaginably dense and hot, particles could have been entangled on a cosmic scale. This would mean that fluctuations in one region of the cosmos could have influenced fluctuations in another, creating a complex web of interactions that ultimately contributed to the distribution of energy and matter. As the universe expanded and cooled, these entangled relationships might have influenced the patterns of the cosmic microwave background radiation, the afterglow of the Big Bang we now perceive as the universe's first light. This hypothesis challenges the traditional view that the first light emerged solely from random processes. Instead, it suggests that the intricate dance of quantum entanglement could have left its imprint on the structure of the early universe. Researchers studying this theory propose that entangled particles might have caused subtle correlations in the cosmic microwave background, offering a potential signature of quantum entanglement in the universe's earliest moments. Moreover, understanding these quantum effects could provide deeper insights into the nature of reality itself. If quantum entanglement indeed shaped the universe's first light, it would imply that the fundamental fabric of the cosmos is far more interconnected than we might imagine. This perspective not only enriches our understanding of the universe's origins, but also invites us to consider the profound implications of quantum mechanics on a cosmic scale. As we continue to unravel the mysteries of the cosmos, theories like the quantum entanglement hypothesis remind us that the universe is far more complex and fascinating than we could have ever dreamed. By exploring these ideas, we move closer to uncovering the truths hidden within the cosmic tapestry of the universe's first light. Shifting our focus from the intricate world of quantum mechanics to the vast and empty expanses of the cosmos, let's delve into the cosmic void theory, a fascinating perspective that highlights the significance of what might seem like nothingness. Cosmic voids are the immense regions of space that contain very little matter compared to the dense clusters and filaments of galaxies we observe. These vast, empty areas might not appear significant at first glance, but they could hold vital clues about the universe's first light and its origins. Imagine the universe as a cosmic web, where galaxies are like nodes interconnected by threads of matter. Between these threads lie the void's vast expanses devoid of stars, galaxies, or nearly any form of matter. Scientists studying these voids have proposed that their presence and distribution could have played a role in shaping the early universe's energy patterns. As the first light emerged, these voids might have influenced how energy propagated and distributed itself across the cosmos. Voids, contrary to their name, are not entirely empty. They contain sparse amounts of matter, and their properties could offer a window into the conditions of the early universe. By studying the distribution and behavior of these regions, researchers aim to understand how the cosmic microwave background radiation, the afterglow of the Big Bang, might have been affected by the presence of these vast, underdense areas. This could provide insights into the initial fluctuations in energy density that eventually led to the formation of galaxies and other cosmic structures. Moreover, the cosmic void theory suggests that these empty regions may have acted as natural laboratories, preserving the conditions of the early universe more faithfully than denser, chaotic areas. This preservation could help scientists decipher the subtle imprints of the universe's first light, offering clues about its origins and evolution. By examining the voids, we might uncover how the universe transitioned from a uniform state after the Big Bang to the complex web of structures we observe today. Understanding cosmic voids not only enhances our grasp of the universe's first light, but also challenges us to rethink the role of emptiness in the cosmos. What seems like silence in the vast expanse of space might in fact carry echoes of the universe's earliest moments. Through this lens, the voids become not just gaps in the cosmic web, but potential keys to unlocking the mysteries of our cosmic origins. Transitioning from the exploration of cosmic voids to another intriguing aspect of the early universe, let's turn our attention to the neutrino oscillation theory. This theory sheds light on the behavior of neutrinos, some of the most abundant yet elusive particles in the cosmos, and how their oscillations might have played a role in shaping the universe's first light. Neutrinos are often referred to as ghost particles because they interact very weakly with matter, making them incredibly difficult to detect. Despite their elusive nature, neutrinos were abundant in the early universe and could have significantly influenced its evolution. One of the fascinating properties of neutrinos is their ability to oscillate or change flavor as they travel through space. This means that a neutrino detected as one type electron, muon, or tau may have started its journey as a different type. In the context of the universe's first light, neutrino oscillations could have affected the distribution of energy and matter in the early universe. As the universe expanded and cooled after the Big Bang, neutrinos, being among the first particles to decouple from the hot plasma, carried vital information about the conditions at that time. Their oscillations might have influenced how energy was distributed across the cosmos, potentially affecting the formation of cosmic structures and the propagation of the first light. Moreover, the study of neutrino oscillations provides a window into the fundamental forces and interactions that governed the early universe. By understanding how neutrinos behave and interact, scientists can gain insights into the nature of the forces that shaped the cosmos during its infancy. This includes understanding the delicate balance between matter and antimatter, as well as the role of neutrinos in creating the slight excess of matter that allowed galaxies and stars to form. The neutrino oscillation theory invites us to consider that even the smallest particles, with their seemingly insignificant interactions, could have profoundly influenced the birth of the universe and the emergence of the first light. This perspective highlights the interconnectedness of all cosmic phenomena, reminding us that even the tiniest details matter in the grand tapestry of the universe's history. As we continue to unravel the mysteries of neutrinos, we may uncover new clues about the universe's origins and the conditions that gave rise to the light that continues to illuminate the cosmos today. Shifting our focus from the enigmatic world of neutrinos, let us now explore another groundbreaking perspective on the universe's first light, the modified gravity theory. This theory challenges the long-standing principles of Einstein's general relativity, proposing alternative frameworks to explain the behaviors and forces at play in the early universe. Modified gravity theories suggest that the fundamental rules governing gravity might differ from what Einstein initially described. These alternatives aim to address certain anomalies and inconsistencies observed in the cosmos, such as the unexpected acceleration of the universe's expansion or the distribution of dark matter. By tweaking the equations of gravity, these theories attempt to provide a more comprehensive explanation for cosmic phenomena without relying heavily on hypothetical components like dark matter or dark energy. In the context of the universe's first light, modified gravity theories offer a unique lens through which we can examine the formation and propagation of light in the early universe. They suggest that the way gravity interacted during those initial moments might have been subtly different, influencing how light traveled and interacted with matter. For instance, some of these theories propose that gravity could have been stronger or weaker in certain regions, affecting the clumping of matter and the subsequent release of the first light. Moreover, these alternative gravity models could explain anomalies in the cosmic microwave background radiation, the faint glow left over from the Big Bang. They offer potential solutions to discrepancies in the temperature fluctuations across the sky, which traditional models struggle to account for. By exploring these modified gravity theories, scientists hope to uncover a deeper understanding of the forces that shaped the universe and the emergence of its first light. The implications of modified gravity extend beyond just the first light. They touch on fundamental questions about the nature of space, time, and the forces that govern our universe. While still a subject of intense research and debate, this theory invites us to reconsider the very foundations of physics, reminding us that our understanding of the cosmos is always evolving. Through further study and observation, we may yet uncover the truth about the forces that lit up the universe all those billions of years ago. Exploring the benefits of Stoicism, we find that it serves as a timeless guide for navigating life's challenges, offering practical wisdom and inner strength. But now, let's shift our focus to a completely different realm, one that bridges the gap between the tangible and the intangible, where the abstract concept of consciousness might hold the key to understanding the universe's first light. This is the theory of the consciousness-created universe, a speculative yet fascinating idea that suggests the very act of awareness might have played a pivotal role in shaping the cosmos. At its core, this theory proposes that consciousness is not merely a byproduct of biological processes, but an intrinsic part of the universe's fabric. Imagine a universe where the emergence of the first light was not a random event driven solely by physical forces, but rather a manifestation of collective awareness or cosmic intention. In this framework, the act of observation, whether by conscious beings or as a fundamental property of the universe itself, might have influenced the formation and propagation of light in the early universe. While this idea may seem far-fetched, it draws parallels with certain interpretations of quantum mechanics, which suggest that the act of measurement affects the behavior of particles. If we extend this principle to a cosmic scale, it opens the door to intriguing possibilities. Perhaps the universe, in its nascent stages, possessed a rudimentary form of consciousness that guided the processes leading to the first light. This could explain anomalies in the cosmic microwave background radiation, where patterns might reflect the influence of consciousness rather than purely random fluctuations. The consciousness-created universe theory also invites us to reconsider the nature of reality itself. Instead of viewing the universe as a collection of inert matter governed by unyielding laws, it proposes a dynamic, interconnected system where consciousness plays an active role. This perspective aligns with some philosophical traditions that emphasize the interconnectedness of all things and the potential for consciousness to shape reality. While this theory remains speculative and lacks direct empirical evidence, it challenges us to think beyond conventional boundaries and explore the deeper mysteries of existence. By incorporating the possibility of consciousness into our understanding of the universe's first light, we open ourselves to new insights and possibilities. Whether or not this theory ultimately proves correct, it serves as a reminder of the profound mysteries that still surround us and the importance of keeping an open mind in the pursuit of knowledge. In summary, we've journeyed through 30 fascinating theories that attempt to unravel the mystery of the universe's first light. From the widely accepted Big Bang theory, which paints a picture of an explosive beginning followed by the emergence of the cosmic microwave background, to the mind-bending possibilities of the holographic principle, where the universe might exist as a projection of a two-dimensional surface, the diversity of these ideas is astounding. Each theory offers its own unique lens through which we can view the cosmos, whether it be through the lens of quantum fluctuations seeding the first light, the multiverse hypothesis suggesting other universes with differing first lights, or the controversial simulation hypothesis questioning the very nature of reality. We've explored ideas that challenge our understanding of time, matter, and even consciousness itself. Theories like the ekpyrotic universe proposing a collision of higher dimensional brains, or the black hole genesis theory, suggesting our universe might have been birthed from a black hole in another universe, push the boundaries of our imagination. And while some theories, such as the steady-state theory, have fallen out of favor, they still provide valuable insights into the historical development of cosmology. Ultimately, the universe's first light remains one of the greatest mysteries, inviting us to keep questioning, exploring, and discovering. As we stand on the brink of new scientific breakthroughs, the possibilities seem endless. So, what are your thoughts? Do you have a favorite theory or perhaps an idea of your own? Share your insights in the comments below. Don't forget to subscribe to our channel and enable notifications for more intriguing space mysteries. Together, let's continue this cosmic journey of discovery.